Now that we have a better sense of some of the potential damages of climate change, let us turn to the topic of carbon pricing. In determining the appropriate tax on an externality, two properties of the pollutant are of particular importance. First, whether it concerns a stock or flow pollutant, where stocks such as greenhouse gases build up over time due to longer half-lives. By contrast, the damage of flow pollutants is near instantaneous and does not persist over much time and seems more accurate for sulfur pollution. For a flow pollutant, the Pigouvian tax is equal to the marginal external damage, as we saw last week. For a stock pollutant, however, the tax should be set equal to the discounted cumulative marginal external damage. We will discuss this discounting shortly. The second characteristic of importance is whether the pollutant is uniformly mixing or not. In case a pollutant is uniformly mixing, the location of the source does not matter for the damage, as is the case with greenhouse gases. For non-mixing pollutants, the location of the source and the vulnerability of different recipients do matter. Here one can think of nitrogen pollution. As shown in the figure taken from Erisman and colleagues, about 5% of nitrogen deposition occurs on land within a kilometer squared radius from the source, and 20% and 50% within 100 and 1,000 kilometer square radius from the source, respectively. One can imagine that this complicates finding optimal taxes, as fairness standards or environmental protection potentially clash with efficiency. An interested reader that is familiar with matrix notation can find a good introduction into these complications in Perman and colleagues. This table from Nordhaus shows that social cost of carbon estimates strongly depend on the choice of discount rate, where we see social cost of carbon close to $1,000 for near zero discount rates, and these estimates drop rapidly for higher discount rates. The discount rate refers to the rate at which we assign a lower value to outcomes that occur later in time. We will go into Nordhaus' model soon, but let us first dig deeper into this discount rate that seems to determine the social cost of carbon. Why do we discount the future? And which rate is appropriate, you may wonder. What reasons can you think of for assigning a lower value to outcomes in the future as compared to monetary value of some required investment today? An introduction by Arrow and colleagues into discounting concentrates on two reasons, one investment-based and the other consumption-based. The former holds that if there is a positive return on investments, then receiving €1 now is worth more than receiving €1 in the future. The consumption-based reason follows if future generations can reasonably be expected to be wealthier, then current outcomes should be weighed heavier than future ones, since an additional euro is worth more to someone with the lower income. Arrow and colleagues argue in favor of adopting a discount rate that declines for discounting outcomes further away in the future, which follows from either a slowdown of economic growth or uncertainty about the appropriate discount rate. A numerical example may help to illustrate the consequences of discounting. Assume that the discount rate is 3%. One would prevent €103 of damage in a year time as long as it would cost less than €100 today. Or similarly, €100 in damage in a year time is worth €97.08 in discounted damage today. By the same logic, some damage further away in the future can be discounted in present-day terms. The same €100 in damage in 10 years is worth some €74, while would the damage occur in 100 years, it would be €5 today. To further illustrate the consumption-based reason behind discounting, the St. Petersburg paradox could be helpful. Provided that future generations will be richer, the consumption-based rationale follows from diminishing marginal utility. Diminishing marginal utility refers to €1 being worth less if someone has more euros already. Now consider St. Petersburg paradox. It refers to an imaginary casino game where you can potentially win an unimaginably large amount of money. The game is as follows. You flip a coin. If it ends up tails, it's game over. But if you flip heads, you win €2 and can flip again. With tails, it's again game over, but with heads, you double your winnings and you can flip once more, etc. How much are you willing to pay to participate in this game? And what is the expected value of participating? That no one is able nor willing to pay the expected value for participating in this game can be explained by diminishing marginal utility of money, subject probability weighting, and loss aversion. I included the St. Petersburg's paradox to playfully introduce infinity. The issue of unboundedness of benefits or damage until undefined time arguably introduces a pragmatic reason to adopt some positive discount rate. Consider a project that costs 30 and a year of installation, but afterwards starts giving yearly benefits of 1 for an unknown lifetime, possibly approaching infinity. Would the project merit public funding? Suppose again that the discount rate is 3%. This is a question of cost-benefit analysis in rather abstract terms. For this hypothetical project, the discounted benefit would outweigh the initial startup costs, and it could deserve public funding. Now, very briefly to introduce some notation used in Nordhaus. So far we have looked into discounting in discrete time, but for some math it is easier to work in continuous time. Imagine ever smaller increments of time, then the discounted value is captured by the expressed integral instead. So what discount rate is appropriate? Many economists have argued for using near zero discount rates. For example, Solovey wrote, "We ought to act as if the social rate of time preference were zero, though we would simultaneously discount future consumption if we expect the future to be richer." And Ramsey, whose rule introduced this consumption-based reason for discounting, argued, "We do not discount later enjoyments in comparison with earlier ones, a practice which is ethically indefensible and arises merely from the weakness of the imagination." Anand and Sen summarize the need for some positive discount rate for integrals to converge and explain how Ramsey's notion of a blissed level of consumption allowed Ramsey to circumvent this problem. In this week's readings, also a call from Blignot and Aronson to use negative discount rates for ecosystem restoration initiatives. They argue that natural capital does not behave like manufactured capital in the sense that ecosystems in healthy states maintain or replenish themselves, and their value is likely to increase over time, at least on par with population growth. Moreover, they argue that the cost of restoration increases when postponed. Finally, while not really an argument in favor of a negative discount rate, Davidson cautions that the social discount rate cannot be inferred from private behavior underlying interest rates. Note that using negative discount rates gives again this challenge of unboundedness, unless we would somehow minimize distance to some assumed maximum level of carrying capacity or ecological bliss. Before turning to the social cost of carbon, let me briefly illustrate why uncertainty about the appropriate discount rate would be reason to adopt a certainty equivalent discount rate that decreases for outcomes further away in time. This table displays the value of $1,000 after T years for discount rates of 1%, 4%, and 7%, and the expected value if we are uncertain whether 1% or 7% is an appropriate discount rate, but equally likely. We see that the discount rate that would produce this expected value, the certainty equivalent discount rate, approaches the lowest discount rate of the set considered for the distant future.